Transformers are a type of machine learning model which learn to encode their input data by learning how each part of that data relates to the entire input. Transformers are a computationally efficient way to encode data, and they can be trained without labels on a large amount of data that is scraped from the web, for example.
You could conceivably have a deep learning transformer model try to make money by generating art that it could sell as NFTs, and then use those funds as a way to pay for its server costs.
Hey, this is Sri.
And this is Will.
Welcome to the Technium, where we talk about the edge of technology and what we can build with it. An optimistic look at the road ahead. Hey, Will, how's it going?
Hey, Sri, how's it going? It's going all right on this end. How's your week?
Yeah, not too bad. Not too bad. I actually, it's been snowing a ton, so this is pretty fun. And I stocked up right before the snowstorm and got some interesting drinks. I went to H Mart.
Wow.
I got this thing. I actually don't even know what it says or what the name is, but the translation at the back is barley flavored soda. So that's what I'm drinking today. Yeah,
that it could be good because it's kind of like a roasted barley flavor. That might be good.
Yeah, I don't know. It has a picture of a farmer holding some, I'm guessing barley.
Wheat,
so I like
or
that.
Barley, yeah.
Yeah.
Well, that's pretty cool. So, yeah. So this week I have something from Trader Joe's. It's a blueberry lavender almond beverage, and I have to say it's good, but it tastes weird because lavender is almost perfumey to me, so it seems like you're ingesting perfume at the same time, so it's a little odd.
That is a pretty strange. Yeah, I've never had any lavender flavored food, so
lavender ice cream is pretty good if you've ever had it.
Oh, I should try that sometime.
Yes. So what are we talking about this week?
So this week we are talking about transformers. Transformers are a type of machine learning model which learn to encode their input data by learning how each part of that data relates to the entire input. Transformers are a computationally efficient way to encode data, and they can be trained without labels on a large amount of data that is scraped from the web, for example. Transformer models have been very revolutionary in enabling computers to do tasks that were previously thought to be incredibly difficult, such as generating realistic natural language and even writing computer code.
Wow, yeah. So I was looking at deep learning and machine learning way back, I don't know when, that must have been 5-6 years ago, and that was when convolutional neural networks were all the rage, and RNNs had only started to kind of come into the consciousness of a lot of computer scientists. And then since then I was just well, maybe I need to go in a different direction for X, Y, and Z reasons. So I completely missed transformers, and apparently this thing is just subsuming everything else. It has just everything that I learned is basically outdated and none of it matters because transformers are the thing.
Yeah, it's kind of crazy. I sort of started working in the space of natural language processing around 2017, and 2017 was when this paper
came out.
That came out. Yeah, Attention is All You Need, which introduced the transformer. And since then, it's just been nonstop, paper after paper, discovering new ways that this type of machine learning model, this architecture can be used. And it's blown every other technique out of the water. I've worked on teams where they were using all types of very custom-built techniques, and then somebody was like, why don't we just try some transformer-based model, and it does way better than what people had been working on for years. And so that's how revolutionary these things have been.
Yeah, I mean, when I was learning about convolutional neural networks, I was oh, it can learn features also at the same time you're training the thing. Woe to the graduate students of the last 20 years in computer vision wasting their lives just designing custom feature recognition parts to input into whatever machine learning thing. You could just train it end to end now. But
yep.
I mean, I guess the laugh's on me because now convolutional neural networks have their weaknesses, and all you need are transformers. So we're going to talk about why is it that transformers had such a big impact on deep learning and neural networks, and kind of what were the main big ideas that were in there, and then what people use it for nowadays and what you could use it for in the future. And then maybe we can talk about whether this is the end-all be-all, or maybe there's something else that would blow transformers out of the water. Because it's not a Technium podcast unless we speculate without any bearing whatsoever, with no accountability. So.
Yes, exactly. So let's dive into it. Yeah, I think, I think a caveat is that we are not a sort of tutorial. A lot of this stuff is very math heavy in its theory,
Hmm.
and even the best explanations for a working programmer are going to be very visual in nature. And so we're going to reference out to some other resources in the show notes. But the big idea that you do need to know in order to understand what transformers are is that machine learning models work on math. They work on processing vectors as input, and they output vectors as well. And so machine learning models, deep learning models specifically, are basically huge piles of matrices stacked on top of each other. And so that's how all of these types of things work. And so traditionally, when you're building a deep learning model, you need to match the architecture of your deep learning model with the kind of shape of the matrices that you are feeding into it. So, like you had mentioned, Will, there were lots of early advances in image processing, computer vision, by taking images and treating them as two-dimensional inputs of intensity and color, which they are, right? Like if you think of an image, it is a grid of colored pixels. And the original way of treating images and using deep learning is to scan them in 2 dimensions and chunk them up into little pieces and run some type of filters and matrices over them and make use of the fact that they are a 2-dimensional structure. And then coming to text is treated as a sequential input, because if you have a sentence is one word after another. It's a sequence of words, for example. And so in order to process that type of input, people were using RNNs or recurrent neural networks, which read each token one at a time and processed them sequentially, as you might do if you were reading a sentence as a human. So that's sort of the lay of the land.
Yeah, that's only natural because like in image and image processing, oftentimes for filters, you have what's called a kernel, and it's like a sliding window. You slide over the image, and that's how you transform it in some way. And it's not a far leap from what people were already doing. It's just that they did it at every layer, and so I can see how that's the case. And then when you look at text, you're like, oh, we read from left to right, and obviously it seems like a sequence. So then you would naturally try to look for solutions that are conducive to a sequential type of processing, because in images, I think with convolutional neural networks, there's no notion of memory, I think, right? Like it's not like it's something that remembers from one image to another. Essentially, you're training like a pure function, whereas for sequential input, these neural network architectures need to maintain some sort of state, as was thought, to kind of process things so that you can relate one part of the text to another part of the text. And so that's why these things kind of originated with those sort of techniques.
Yeah, exactly. So people were just using the natural shape of the input and saying, we're going to make a neural network architecture which matches that in some intuitive way. And that was all fine, especially in the image processing world, because like you had mentioned, that there isn't this sense of maintaining some state or memory while you're processing an image. The convolutional neural networks were sufficiently fast and parallelizable so that in the computer vision community, they were actually making incredible gains as GPUs got faster, as they were able to do better optimization techniques. There was this explosive growth in the state of the art and the performance on their tasks that they were trying to do. But at the same time, the natural language processing community, the NLP community, was sort of hindered by the sequential nature of RNNs. Mm-hmm. Because the thing is that these deep learning models run on graphics processing units, GPUs, that are really good at parallel computation, but they are slow, or you're not taking advantage of their capacity if you're doing sequential computation. And that's what people were doing with RNNs. And so
RNNs being represents recurrent neural networks, for those of you that want to search for it. Yeah.
Yes. So that's where the transformer comes in. The transformer is a way to basically process the input, a sequential input, by looking at it all at once. And so that's a little bit hand-wavy, but transformers use what's called a self-attention mechanism, which means that rather than processing one word at a time, it takes the entire sequence as an input and then uses what's called an attention mechanism to focus what word it's looking at in order to model the relationship between the different parts of the input, or the different words in a sentence, for example. And so that basically meant that rather than having a loop, you could actually just process all of its input all at once. And that was a huge speed up just in terms of processing time. And there are other benefits beyond processing time, but if that was the only thing it contributed, it actually would have been revolutionary in and of itself.
Right. And so to reiterate, one of the things about text processing is that people conceived of it as something that you needed to do sequentially because we conceived of it as reading text words left to right. And then so that means the RNN and like the LSTM, the long short-term memory, constructions are always such that if you're trying to calculate the nth token with the recurrent neural network, the RNN, then you needed the n-1 result from the previous token. That means that you need to process them all sequentially. There wasn't a way in that architecture to parallelize it at all because you needed the previous step. And and the reason why they wanted this sort of stuff chained was that if you have a word, it's likely referring to not just the words that are next to it, but something further on. Like, for example, you have a pronoun it, and it might refer to something that is like 5, 6, 7 words away. And without this kind of state memory with the sequential model, there wasn't previously a way to give the neural network an ability to relate these two things that were distance far apart. But with the self-attention mechanism, it gave people the ability to much more easily relate two things that are far apart, and you could learn them in parallel. And so these were kind of a you can have your cake and eat it too sort of thing.
Yeah, exactly. That's really well put. So in addition to the performance implications of using self-attention to process the entire input at once rather than using a loop, transformers also solve the problem of the fact that when you're processing a very long input sentence, you need to keep track of all of the tokens that you've seen so far. And if you have a very long sentence, then you might forget, or when I say you, I mean the machine learning model might forget what it's seen earlier on. And even though that information is potentially useful in let's say classifying a sentence. So if you have a spam classifier and it's classifying a very long email, then this becomes a problem because the longer the email gets, the less able it is to consider the tokens, the words at the beginning of the sentence, and rather it bases its decision on the tokens that it's seen more recently. And that's not a desirable property. Ideally, you want it to be able to consider the entirety of its input at once, regardless of how long that input is. And so transformers and the self-attention mechanism solve that problem by basically just keeping the entire input in memory, and rather than forcing the machine learning model to somehow be able to remember what it's seen before, it just says, just look at the entire input and then focus on the parts that you want to.
Yeah, and then the reason why it's called attention is it's a metaphor to what we perceive humans do. When we look at a part of an image or part of a sentence, like we're focused on that part of the sentence and how it relates to some meaning that we have in our head. And similarly, attention is effectively a series of weights, and these weights are learned. And so when you're processing a token, how is that token related to, I guess, an embedding, right, that we have in our head? And embedding is just, you could just call it meaning. Like it's a parameterized meaning in that is somewhere in some vectorized space in the machine learning's head, I guess is one thing that you can say it.
Yeah. So that's one key difference that the transformers introduced was self-attention. The other interesting thing that people don't talk as much about is that transformers are agnostic to the structure of their input. And what I mean by this is that previously people were treating sentences as sequences of tokens. And transformers said, I don't know anything about sequences. Transformers just take all of their input as a huge set or a bag of inputs, bag of fragments. And so transformers don't know anything about sequences. They don't know anything about grids of pixels. All of that is actually encoded by this other mechanism called position embeddings, which basically take all of the fragments of your input and then add a learnable position embedding, which allows a model to learn where something is. And so this is a little bit abstract, but basically what this means is that it allows transformers to generalize to all kinds of input that have different types of structure. And so this is one of the reasons why transformers increasingly are being used for things outside of sequences, and in fact are taking over some of the computer vision community. Because transformers are agnostic to the structure of the input, and the structure of the input can be learned through these position embeddings, now transformers can run over sequences, they can run over grids, such as images, they can potentially run over graphs, and any other thing, as long as you can sort of encode it using these position embeddings.
Are these positional embeddings, are they relative to everything else, or are they some, I guess, like they're some sort of vectorized space that relates the position of one token versus all the other tokens, however you define position, right? And so in a text, it might be like distance to every other word or something like that.
Yeah, so people use different things, and there are lots of different techniques. Some people use a sine wave. There are other architectures where this position embedding is entirely learned, and so you actually don't say you don't impose any structure upon this, and it just sort of learns the right thing. So there are different ways to do it, but basically the idea is that rather than having the machine learning model know something about the position and treat things differently, it sort of learns that.
Right, and so basically you're splitting up the functionality of the, like what we usually call embedding, you could say is the abstract meaning of a token, or like whether it's a word or like part of an image or something, versus its positional embedding, which is like how it relates to every other thing in the data that you're feeding it, right? And so these are two separate things now that you then merge together to be able to send through the transformer architecture.
Yeah, exactly. Transformers use self-attention, they use position embeddings, and that makes them fast. It makes them agnostic to the structure of their input. They can take sort of any type of input. And so with that, it solved a huge set of problems for the NLP community. And the
underdogs really just got a leg up on there, right?
Yeah, exactly. So, transformers, they broke performance records, both in terms of the computational performance as well as the performance on some of the key metrics and benchmarks.
Yeah.
And then there were a ton of follow-on papers to the transformer that were built on the transformer architecture, where they used transformers as sort of a Lego building blocks that they stacked on top of each other, and they added other types of components to. And these are names that people have probably heard. So one of the follow-ons to the transformer was BERT. BERT was one of the first natural language processing models that was pre-trained, that the creators at Google Brain basically trained BERT on this huge corpus of data. I think it was Wikipedia, or it might have also included the web data. And you could just take BERT off the shelf, and it would work great.
So when you said it worked great, you mean that you can take BERT off the shelf, pre-trained model, and apply it to any number of different domains, and it would perform relatively well. Because before, to have one model trained in one scenario perform well in a different one was a difficult thing. Like it was still relatively brittle, where you would train it specifically for something, you get great results, get your paper, people think that it's awesome, but if you take that same model and try to apply it somewhere else, like it fell apart, right? And so this was the surprising thing, that BERT seemed to do pretty well across different domains, at least in NLP, right?
Yes, in NLP. This was actually a very commonplace thing in computer vision, where there were some base models like AlexNet, VGG, things like that, which worked off the shelf for many image processing tasks, but this was not the case for NLP tasks.
Right,
and BERT was one of the first ones that brought that in. And then, of course, the famous GPT family of models, where GPT-2 was probably the first one that OpenAI published that had a lot of fanfare because it worked decently well. It appeared to work decently well. And then they continued onwards with GPT-3, where they just took the same exact architecture and they just said, we're going to stack more and more transformers on top of this thing.
Why don't we just pour gasoline on it? Gasoline being lots of data. But yeah, like this architecture seems to work. Like let's see what it can do if we like turbocharge it.
Yeah, so it turns out if you throw more transformers and more data on the problem, things just continue to get better. And so GPT-3 is a transformer-based model, which is actually surprising in that it ends up learning things which make it a significant step change away from simply some of the simple NLP models before it. Specifically, GPT-3 has ingested so much data and basically learned all of the internet that now you can simply get responses for a particular task simply by asking it to generate text that looks like that kind of output that you want. You don't even have to train it traditionally. You just say, here's a prompt, respond to this prompt, and it will generate text that looks like that. So you can say, generate text in the style of Abraham Lincoln talking about machine learning, and it might actually do this, so it ends up being significantly different than all of machine learning models before it, in that it has a sort of generative capabilities that allow it to solve very generalized tasks.
Yeah, it's one of those, I guess, facts of innovation where if you make something quantitatively different to an order of magnitude, then it becomes quantitatively different. And that's exactly what you're saying here. Like if you make something 10 times faster, people will start using it for things that they never dared using it before. And that changes the nature of things. Like if cars or transportation if cars made transportation 10 times as fast, I don't have to take a horse and buggy to go visit people, then all of a sudden, like maybe there's a new market that comes up where you can have restaurants because you go out with your friends all the time. Like I'm making something up, but that's effectively what you're saying. Yeah, and like I've tried GPT-3 and it's kind of amazing the types of things that you can generate. You can ask it to generate things for you as a way of looking something up. So like you can have fun with it, say like, make a speech or like you can talk the housing crisis, but in the style of Chris Rock or something like that, right? And it'll like do its best to generate that for you. But also like if you want the answer to something like what are the, like write me a paper on side effects in programming, like it'll generate text that might give you parts of answers. And so it's up to you as a human to like filter it out, but like it does amazingly well there. And so I guess to your earlier point, like it's surprising that you can just throw more data at this thing and stack it higher and higher, and it does better, because previous neural networks had a problem with this. Like you would have vanishing gradient problems if you just stack really deep. Like people tried deep neural networks before and it failed because they just couldn't figure out how to train the thing. It turns out we just need more data and like faster machines. So like what's the case with transformers, that you can just throw data at it and just stack it higher and higher? Because that's surprising.
So I think that the transformer builds on top of a lot of the learning that was happening in the computer vision community, because it turns out that the same principle also worked for computer vision for CNNs. So CNNs got better and better by people saying, let's throw more layers on it. And things got absurdly deep, like hundreds of layers deep neural networks. And performance just got better and better. And the way that they prevented these problems with training and with sort of numerical instability is that they had a lot of mechanisms. These are sort of uninteresting, but some things that I can name drop are like residual layers and batch normalization.
Oh, I see. You're right. That. So a lot of times it's like the actual mechanics in the neural network made the calculations unstable, and so taking the learnings from there, they just reapplied it to these.
Yeah, exactly. So, and it turns out to work very, very well. And there's even a paper, the unreasonable effectiveness of big data, which sort of goes into this. It predates a lot of this deep learning stuff, but
right.
The thesis is basically that don't be too smart in trying to encode lots of smart features. Use your human intuition and build better and better models. Like find a type of core model architecture that works, stack it really deep, throw lots of data at it, and it'll do better than you think. And for a long time, this eluded the NLP community because they weren't able to find that core building block that was computationally efficient to stack this high. And the transformer introduced that, and then all of the learnings that were available from the computer vision community, again, immediately translated. And then within the span of just a few years, the transformer was published in 2017. And since then, there has been incredible growth. Like this, it's only been just over 4 years.
So as an aside, 2 questions. One, do you know where the team that came up with the paper for attention, like, do you know where the inspiration came from at all, as an aside? It's okay if you say no, but
no, I actually
okay.
don't.
All right. And then 2, like, how DeepMind made a lot of inroads into protein folding? Was it also using like a transformer like architecture, or no?
I actually don't know that either.
Oh, okay.
Probably just have to cut these asides out.
Yeah. No, because one of the things is just that they blew everybody in like the protein folding community out of the water. Like it's the first time I saw something where the people in biochemistry was like, there's no need for us to have a conference anymore because this is solved. So,
Yeah. Actually,
by outsiders, no, like by people that have no idea, have never really studied the problem,
yeah.
which is
Yeah.
amazing. So, anyways,
Yeah, it turns out that this is the direction that a lot of the machine learning and deep learning is going. Is that the lesson is don't be too smart, don't be too cute. Just use simple stuff, and it'll sort of blow everything out of the water.
yeah, didn't that come from Norvig or something like Peter Norvig? He was just saying just throw more data about.
Yeah.
I don't know, whatever. Anyways,
Yeah.
let's move on.
Cool. Yeah. So Transformers made a huge splash, needless to say. And so what does that mean? What does it mean now that we're in this new Transformer world? I think it means a few things. One really, really interesting thing that people kind of sort of talk about, but I think is slept on, is the fact that Transformers are structure agnostic. That they don't care if your input is a sequence, a grid, a graph, whatever. If you can somehow learn to encode these positional embeddings, you can have a single type of machine learning model which can encode any type of data.
Yeah.
And this has actually been used in a new type of machine learning, which is called multimodal machine learning. We talked about this a little bit in the Clip episode, Clip and DALL-E, where Clip learns to represent both images and text in a shared embedding space, which means that you can compare the similarity of a piece of text with an image and say, does this text describe this image? And this is what we mean by multimodal. It's comparing two modalities or two types of media, in this case, images and text. And the transformer makes this really, really easy because you don't have one type of machine learning architecture that's suited for one type of data and then another that's suited for another type of data, and then somehow merge these two and reconcile these two. You can just have it be transformers all the way. And this is very, very interesting because the world itself is sort of multimodal. The concept of a cat, for example, can be represented visually. It can be represented with text. It can be represented by a video, a 3D mesh, whatever it is, the sounds it makes. And so multimodal is kind of the future if you want to build machine learning models that know more and more about the world, kind of giving it more and more senses.
Yeah, essentially Transformers is the Docker of the machine learning world, or like the internet protocol of the machine learning world, right? We've used this term before. It's the narrow waist, right? Like when you have like N things that got to match to M things, then you have this combinatorial explosion of like implementations you got to do. Like we got to translate one to the other. But like if you have one common intermediate representation for any of these things that you have to translate N of to the M of, then it makes it a lot easier. And that's effectively what transformers give us, right? And even more so that it's multimodal. And one of the tweets that I saw are Andre Kaparthi, who is, I think, director of AI at Tesla now. He talks about how this is a unifying force for people in machine learning, because before he couldn't really read a lot of the other papers in other machine learning subfields. But now that transformers are like subsuming everything else, he's actually able to take techniques in other subfields of machine learning and apply it to vision, which is what he's doing with the driverless cars at Tesla. And it goes the other way around. So there's a lot of cross-pollination that way because they have an intermediate representation that's available for them to use.
Yeah, totally. And I imagine that even beyond the individual researchers being able to cross-pollinate ideas, which shouldn't be understated, by the way, because it turns out that when things are in sort of silos by domain or by vertical, then progress is sort of unnecessarily hindered versus when you have a world where people can freely take ideas, and not just ideas, you can actually just take straight up transformers and apply them to all different kinds of things off the shelf. And so I think that's one really interesting idea. And I think that specifically in the case of Tesla and self-driving cars, I imagine that being able to have a common building block that is able to process all the different senses. If you think about self-driving cars, they need to process vision. In the case of LiDAR-enabled self-driving cars, they have 3D point clouds. They probably process audio as well as many, many other things. It's probably nice to have a shared building block that is able to process all of these different types of media rather than having individual customized ones.
Yeah, so that makes me think that you can actually get really specialized hardware for this that specializes in transformers rather than kind of putting them on top of GPUs. Is that something that you've heard of people doing? Or like does everything reduce down to like GPUs because they don't, you're just pushing stuff in parallel to this hardware?
The folks at Google have these specialized hardware called TPUs. They're called tensor processing units that are a little bit more specialized than GPUs in that they excel at very fast matrix multiplication, which is what transformers are based on. I think beyond that, everything just reduces down to matrix multiplication. So I don't see that there's a huge transformer-specific hardware that is necessary, but maybe, I don't know.
Okay.
Yeah. So that's one big thing. And I think the other big thing is that these are, like I mentioned, incredibly computationally efficient. And what it means is that you can train transformer-based models on huge amounts of data that you take from the web, that you take from driving self-driving cars around and collecting recordings and things like that. And the nice thing is that in the case of the research community, you can train a large model once and then release it to fine-tune. And so now, unlike previously, the NLP community is not constantly training their own models for every individual type of task, like we said. And so rather, they're able to build on top of each other. And so this is why, for example, in the case of GPT-3, people are very rarely now building customized NLP models that are classifying sentiment or something, and then collecting huge amounts of data and then training sentiment classifier that says, is this review positive or negative? Now that GPT-3 has sort of slurped up all of the text on the web, you can simply ask GPT-3 and use, like we said, use prompt engineering to get GPT-3 to output just using its normal generative capabilities. And so this is a new area of research called zero-shot learning. There's a paper that came out of Stanford AI where they describe these types of models as foundation models, meaning that everybody uses them. And there are a lot of sort of ethical implications where if these foundation models are found to have biases and things like that, then it biases the output of everybody who uses them. So it's kind of like an open source now in that way where you have this dependency risk. If the thing that you depend on has some security vulnerability, let's say, then that now your application has security vulnerability. Similarly, if there's some kind of problem in these foundation models, it affects all of the downstream users. And so there's a lot of research on that. So those are some of the risks. But overall, I think that it lends to reuse, and it makes it so that this kind of power is democratized rather than having it be only available to those who have a ton of data to train on.
Well, I am surprised, I guess, that it's deep learning is in the state that it is now, because I think it was hard for me to imagine how they were going to get it to compose with each other, or like how they were going to make progress after a certain amount, because it seemed like all the advances have been slurped up by CNNs and then they were plateauing. And so good thing for that attention paper, I guess, however they got the inspiration for it.
Yeah. So I think overall, the improvements of the transformer have been huge in NLP, and like we sort of alluded, they are now eating up some of the gains in computer vision, again, because transformers, they don't care whether something is an image, because they don't care about the structure of the input. And so transformers are increasingly replacing CNNs. There are papers coming out showing that vision transformers are now reaching state of the art on a lot of the computer vision metrics as well. And so, we're in this new world where maybe, I don't know, it's actually hard for me to say. Is there something that will beat the transformer? I mean, probably. But I think for now, we should sort of bask in this renaissance of everything being sort of mutually compatible, having this sort of free trade of information between these different disciplines.
Yeah, that's pretty exciting, because usually in different fields, you get 2 or 3 different theories that seem incompatible with each other. I mean, in physics, it's one typical one where they're looking for a grand unified theory, and in programming, there's people like imperative, functional, and relational, and they're not exactly unified in a concrete way. So it's pretty exciting that people in machine learning have found like a unifying representation to machine learning, I guess.
Yeah, exactly. So that's sort of all of the stuff that's grounded in reality. I think we covered all of the history and the theory and some of the state of the art. And so now I'm excited for our favorite part, which is we say, well, we all this stuff exists. What does it mean? What can we do with this? Like, what does it mean for the world? And so, upon hearing all of this stuff, what do you think?
Yeah, I had to think about this for a little bit. Like, what does it mean in a world where transformers are prevalent? And I think the knowledge about transformers have yet to filter out to other tech communities in general. And so I think it's a little slow on the upshot. But one of the things that I thought about was whether it could be used for compilers. Because with compilers and interpreters, you don't convert directly down to machine code anymore. Usually there's some sort of like intermediate representation or IR that you're converting your code into before it can be compiled down to bytecode of the various machines or virtual machines that you want to target. And so people have IRs in compilers, the same reason why you have Docker or Internet Protocol like IP, and same thing with transformers. And so it's so that you have a narrow waist, basically. So you don't have to write all different combinations of N to M. And so what embeddings really reminded me of was that it was an abstracted space of meaning. Like you have some sort of like vector representation of meaning in space, and it's spatially related to everything else. So if two things were close in meaning, they were close in that embedding vector space. And so it made me wonder if embeddings could be used as an intermediate representation of some sorts between programming languages, so that you could generate bytecode for different virtual machines that you wanted to target. Like, it seems like it's possible, but I'm hand waving because like like people have what's that thing that people are using to generate code inside of VS Code?
GitHub Copilot?
Yeah, Copilot. And so if that's possible, you should be able to generate bytecode with it. That doesn't seem too far-fetched.
Yeah, I think that could be interesting because there are a lot of languages that, for example, haven't yet been translated to the JVM or something, or WASM. At this point, actually, a lot of languages have been translated to those, but that takes a lot of manual effort. And so, maybe I wonder if there's a way to frame this as a translation problem where on one side your input is in the language of some programming language, and then your output is the output of your target platform, let's say WASM, and then you train a language model or based on transformers that knows how to convert one to the other. And the nice thing is that you basically have infinite training data, because you can just take all of the source code that somebody wrote, let's say in a language that does have a WASM target, so like let's say Rust, and then you can actually just run the Rust to WASM compiler and compile it to WASM, and then you feed that as training data into this machine learning model, and then your job is to fine-tune maybe a small subset of your own language, and then see if it can basically make use of all of the things it learned from the other language's compiler and somehow translate it and benefit the compiler that you're trying to write.
Yeah, and so that seems perfectly feasible. Also, another thing is that dream of being able to write in whatever language you want within a company. So maybe if all compilers compiled to these common embeddings, then it doesn't really matter. Like in a single code base, even in a single file, you can just write different languages as long as it's like fenced off. This part is PHP, this part is Ruby or something like that. Then perhaps that seems entirely possible. It'd be a giant mess organizationally, but that seems entirely possible.
Yeah, I think it's interesting. I think
so that you don't need FFIs anymore if everything can be converted into embeddings. Maybe anyways, you were saying.
Interesting. Yeah. No. I mean that's a sort of next level, because I was thinking that you use the transformer model to target, some machine language or some other intermediate representation, such as the WASM runtimes representation or something like that. But you're saying even like, let's just forget the WASM runtime. Let's just run code based on like the embeddings of a particular thing.
Yeah, because you don't need the intermediate representation written by humans anymore. It's just whatever it is, just write it into the embedding, and then you can design whatever hardware you want, and then be able to convert whatever that embedding is to the bytecode for that particular machine, whether it's virtual or not.
Yeah, I mean, now that we're completely in the realm of speculation, there are this idea of what are called neural Turing machines, and the neural Turing machines are this idea that you represent the sort of memory structure of a Turing machine, like a theoretical computer, basically using matrices and vectors and things like that. And so rather than having direct memory lookup to a particular address, you use this machine learning model and attention and things like this in order to look up data in a matrix. And so I wonder if, forget the whole computer itself, like what if you compiled a language down to these embeddings, these runtime embeddings, and then you made an architecture and combine it with a neural Turing machine, and you just have a computer that just runs on matrices and vectors and embeddings and things like that.
Yeah. So this is what I was asking you about earlier with like could you have specialized hardware for this stuff? I think this is where I was kind of getting to. Instead of like everything being on the von Neumann architecture, like could we do this sort of thing? Actually, there's a paper for those of you interested, like can programming be liberated from the von Neumann architecture? And in it, Bacchus of like the BNF, like Bacchus Noir form, that guy, he was lamenting the fact that like back in 1978 or something like that, that like programming languages are just suck hard and like didn't have enough mathematical guarantees and not enough efficiency because of the von Neumann architecture. Like you have a CPU on one hand and like a whole bunch of memory, and you're just shuttling like these words back and forth along a really narrow pipe, and most of those words have nothing to do with the data itself, but mostly the names of data. And so you're just shuttling back and forth. And so instead, if you could construct like a different kind of hardware that was more conducive to say functional programming, because it like the hardware itself dealt with the mechanism of functional programming directly, then could you gain efficiencies? And like I haven't really looked into it, but apparently some people attempted to build Lisp machines, which are like hardware that is very catered to running Lisp. And so I think this is going back to our Alan Kay episode, which is that quote that he had about people that want to really write software would make their own hardware. And this is what he's talking about with, you get that virtuous loop where you write applications in software, have a platform, and that informs the hardware that you should build, which then makes your software easier. But instead we fell into this world where we just made the old architecture faster and faster, to the point where like it's at a point where we basically just have the same von Neumann architecture from the very beginning, and that's kind of gotten so fast that it's subsumed every other design that could have been possible given what we understand about software today.
Yeah, I mean, I think that this is probably an interesting area of research that people are probably exploring, because the database community is using different types of machine learning to optimize queries and improve the efficiency of database systems.
Yeah.
And so, yeah, there could be some room there. There's a lot of interest in sort of machine learning for systems where, I don't know if it's exactly along the lines of what you're saying, of actually just exiting from the von Neumann architecture and then using, matrix multiplication all the way down. But I think that there is an opportunity, I think, for at least, optimizing bytecode or doing different types of things, and maybe putting a machine learning model in the loop in order to even do things like maybe JIT compile code or something like that.
Yeah, it's time to bring Seymour Cray back. I mean, like, he's been working on vector machines for those supercomputers, and they've only found niche applications while he was around. So yeah, go figure. Yeah, so that was my kind of thought of where these embeddings would occur. And so before I go further with other speculation, what about you? Like, where, given that you work in the field, like where do you see kind of the second and third order effects? Like, what if transformers were pervasive and people can use them on all sorts of, like, what would the world look like?
Yeah, I mean, I think one thing that's an interesting implication of multimodal architectures is that you could have multimodal training, and you can imagine that you train machine learning models the way that I imagine a baby learns. When a baby or a child is going through the world, they see something, they hear it make a sound, they hear somebody say, "Oh, there's a cat." They hear the cat meow, they see the cat, they maybe touch the cat, and so they use all their senses in order to get at what a cat is. And they do this all sort of simultaneously, right? It's
without
not like
labeled data either, right?
Yeah, that's right. Without labeled data either. And so it's not like there's a separate phase where they first learn what cat looks like, then later they only learn what a cat sounds like, and then later they hear somebody say the word cat. It all just happens at once. And so I think it'd be very interesting maybe to see what that would look like for a machine learning model where it takes a multimodal input and processes it using transformer. And so maybe the machine learning model watches all of the YouTube videos. Maybe it lives on a robot, and that robot navigates through the world and has cameras and sensors and things like that, whatever it might be, and see if it can learn all of its senses at once using a shared architecture. And then that shared architecture, the sort of embedding cat, captures not just what it looks like, but also what it sounds like, what all the different things that came through all these different senses.
I see. Huh. So then what would you use it for? I mean, that's the kind of the mechanics, but like what are some like concrete applications for multimodal?
Yeah, I mean, I think there are many. It's a little bit speculative at this point, but you can.
Well, that's why we're here.
That's why we're here. Yeah, that's right. No, I mean, I think that one of the interesting things is that, let's say that you've taken, all of the web, and so you understand sort of words. You can't use your understanding of words now to answer questions necessarily about what's happening in a video, because even though you might have two transformer-based architectures, one that is able to process video and one that has learned all of the words in the world, those two are not sort of shared. The knowledge cannot be easily shared between those two. And so if you have this sort of multimodal training, then what could happen is that you could then ask questions about what's happening in this video. What part of this video does the cat jump? And without any sort of labeled data, because it knows, you've trained an architecture, you've trained a model that knows about cats, it knows about, it's seen them jumping, all of that. You can basically use language to steer it towards finding answers in videos, in pictures, in other types of things.
Oh, so you should be able to query inside of media that traditionally escaped search. Yeah, I see. So then this could be applied to all different kinds of media besides images, videos, and sound. Like, what other forms? Like, I guess that covers it all. But I mean, because we don't have smell-o-vision or anything like that. But like per se, if like people thought it was really important to encode smells or something like that, you could get it to go either way. I guess there are things in which we typically don't think about being able to generate that we might be able to do. And we talk about this in the clips and Wall-E episode, where you can type in words and then get it to generate a image or a video. And so you could presumably type up a script and have the computer generate a movie.
Yeah, exactly. So I think that there are a lot of potential for generative media. I think there's a lot of potential in using transformers actually for music. So we didn't touch upon this, but there's a lot of interest in applying transformers for generative music. And so I can imagine that if you have really multimodal transformers as well, you could even ask questions of music like, what are all the songs in the Spotify library that have fast drums and female singer or something like that, and you'd be able to kind of query all of those, or like maybe you're trying to find songs for your soundtrack, and you can say what are all the sort of love songs, 80s love songs that have a particular type of synth and or whatever. And you could do that today if you have these hand-labeled datas on every single song in the entire library, but you probably don't want to do that. You might just want to use, pre-training and multimodal training in order to solve this problem.
Ain't nobody got time for that. Wait, so then what do you know if these transformer models can learn online, or is there like a strict division between training and inference?
I don't think that there's anything preventing them from learning online. I haven't read too much on the literature about that being a thing, just because they also need so much data that you kind of have a distinct training and inference phases. But yeah, I don't see why you couldn't do this online.
Yeah, I guess I was asking in the sense that you could conceivably have a deep learning transformer model try to make money by generating things that would make it earn money. So it could generate art and try to sell them as NFTs, and then based on the feedback of what humans might like, then as part of the training, or maybe like it reads in Twitter as the zeitgeist, and it turns it into embeddings, and then generates art that it could sell as NFTs, and then use those funds as a way to pay for its like server costs.
Yeah. I think we talked a little bit about this in some previous episode where there was a DAO that was trying to do this, but with humans in the loop, where they were trying to use a generative model similar to DALL-E that they feed it in a description of a piece of art. It'll generate that. They try to mint that as an NFT, and then they use that as sort of feedback to steer the model further. Yeah, I mean, I don't see any reason why you couldn't just make that end-to-end work and have the machine learning model every week just like use the feedback that it collects to tweak the output or something like that.
Yeah, because like I guess that would venture into like legal status or legal territory. Like, would the machine learning model be able to own property? Because I guess that probably won't happen, because people that create these things would want to own whatever like productive thing the machine produces. But I guess I could conceive of self-driving cars as the first non-human citizens in a country in which they earn their own keep, right? Like, they would drive people around to their different destinations and then earn money as a result. And maybe if banks won't open an account to non-humans because they can't do KYC, maybe people will be willing to give them cryptocurrency. And then the cars would be able to maintain themselves by driving into auto shops and paying in cryptocurrencies whenever they need an upkeep. And so that way it's a self-maintaining cycle where they want to upkeep the car itself, and then their training is to just drive people from place to place. And then I guess if that's perpetuating, I can see that going on for decades, if not centuries, because then the machine would keep replacing its parts. And it would be that question of, are you still you, even if all the parts are replaced? And so if we somehow get flying cars in the future, maybe like the Honda Civic of today is some flying car of the future, but it's still the same machine learning entity that's running all those parts. It's a little bit of a weird thought.
Yeah, no, it sounds really, really far-fetched, but it's not too far out of the realm of...
It's not entirely inconceivable given what we know, right? I mean, there's definitely a lot of forces that would be against this, like legal and, like ethical, that sort of stuff. But it doesn't seem far-fetched that you should be able to close the loop on this. And same thing with like web design. Like, I can imagine machine learning agents that live solely online, and their job is basically a marketing agency. And so people would go to them to design web pages to sell, I don't know, whatever doodaggy, and then they would just generate landing pages for people to look at.
Yeah. Yeah, actually, so one of the sort of killer app demos that people made for GPT-3 that made a huge splash was that somebody made a demo where you could type in, like, I want a web page with a red background and, a button that says checkout or something. And it would generate like a React DOM tree that would basically match that specification. And so there was this, all this hype that is programming over, like, do we need programmers anymore? Because now you could just do this. Like, do we need React developers anymore? And,
maybe less than we thought we needed.
Yeah. So I think the answer is probably, no, you can't get rid of all of the React developers, but yeah, you can probably get by with less than you needed, or have some natural language interface that does a lot of what the low-hanging fruit that people do. And yeah, like you mentioned, it's a sort of a stone's throw from there to, can you have some type of generative model, transformer-based model, for example, that generates web pages, and not just web pages, maybe it generates the layout of the web page, the copy on the web page, and then you're able to give it feedback, or rather than you giving it feedback, it's able to observe feedback from, the click-through rates and things like that, and then tweak its output. So basically doing what a human would be doing, A/B testing things, but it's just doing it itself because it has generative capabilities, and it's able to also read the metrics.
People better earn their keep at FANG companies before the good times end, I guess. I guess
so.
Yeah. I mean, programmers aren't going to go away. I'm pretty sure of that, but probably we might need less than them. But then again, like one of the things that has been on certain thought leader programmers in mind, I guess, for example, Jonathan Blow, he probably wouldn't like me calling him a thought leader, but Like one of the things we worry about is just how complex programming has become, and like are there ways to simplify programming? But maybe with these deep learning models, like we can increasingly generate more and more capable programs and more complex programs that then become entirely out of reach of most programmers, and so that could also be a possible future.
Yeah, yeah. I think that one interesting trend that's happening is that these deep learning models and specifically transformers are eating the jobs of machine learning researchers first. So it's actually not that they are putting McDonald's workers out of a job.
Right,
They're actually
right.
putting machine learning researchers out of a job because,
That's
like we
interesting.
mentioned, with zero-shot learning, you don't need to hire a machine learning expert who is going to train a classifier that classifies tweets as spam or whatever.
Yeah.
You can simply get by using prompt engineering. So if you have a foundational model like GPT-3, you can, like we mentioned, engineer your prompts in such a way to elicit that model to give you the answer that you want. And so now you don't need as many machine learning jobs, deep learning jobs. And so, yeah, similarly, I think with programming might go in a direction such that the hard part about programming is in the prompt engineering. Can you phrase your problem domain, and can you phrase the specification of your problem in such a way that you can elicit this machine learning model to solve your problem effectively? And that still takes skill, but now you need far fewer people doing that.
Huh. Well, and I guess you don't need data cleaning anymore because you don't need to label any of the data or anything like that. Do you still?
Yeah,
or
you
maybe
don't need
garbage in, garbage out. So I don't know.
Yeah, so with prompt engineering, a lot of the time what you do is you give a few examples. So you say, prompt, classify tweet as spam, examples, and then you give a few examples, right? Like, here's a tweet, spam, here's another tweet, not spam. But the thing is that because this thing is a few shot learner, meaning that it doesn't need tons and tons of training data because it has learned so much from the internet.
Right.
It can basically, with maybe 5-10 examples at max, get the gist of what you want it to do, and then actually be able to generate for future questions that you ask it. Yes, this is spam. No, this is not spam. And so, yeah, data cleaning, maybe not, because you actually don't have a ton of training data that you need to feed a few shot learner.
Yeah. Huh. So then I guess what are all the, well, I guess you don't need to pay machine learning researchers like $1 million a year anymore. So.
Yeah, I mean, if you're a startup, you can actually get access to GPT-3 and be able to build actually quite powerful things without having to hire any machine learning researcher at all. Yeah.
Yeah. That seems to be true. I don't know if that many startups leveraging that though. Is it just that it's unknown, or it's that the problems don't quite apply to a lot of things, or people just don't know about it yet?
I think it's still coming online. OpenAI just opened up API access to GPT-3 to the general public, just a few months ago. And so, yeah, I think things are going to get even better and better over time. Yeah.
I see. Huh. And then I guess for me, I was thinking about how you get machines to talk to each other, and maybe transformers would be able to help with that, because a lot of times the way that we do it across the web is that we have humans engineer some sort of API and we throw it up there, whether it's REST or GraphQL, and then we write a whole bunch of documentation, and then some other engineer on the other side then reads this documentation out of band on the other side and then does some implementation. And it's like shit work that nobody ever really wants to do, but like that's a vast majority of like what we end up having to do. And so I'm wondering if the communicating between two machines that have their own internal schemas and ways of representing data, whether you can communicate not the program itself, but the data that it has into embeddings, so that it can communicate this reliably across the network. Reliably, not in the sense of latency, but in the sense of data accuracy to the other side, without having to write an API. Like that would save hours and hours of work. I have to say, like, as a web developer, I spent so much time just doing integration. I've always hated it.
Yeah, I think there are a few steps to get there. But one thing that is interesting is a callback to our previous episode, was that we were talking about what if you had self-healing APIs, because if you change some minor schema between one version and another, then the computer on the other side says, I don't know what to do with this, even though it might be a very minor transformation, right? Like a key changes, or rather than nesting, rather than having only one, object, top level object of the response, you have a list of objects or something. And so can you make something resilient to that type of transformation? Maybe you can if you use some type of transformer based few shot learner, where what it does is that it'll take a few tries. Like it'll maybe send a request and then see what the response is, and send a few other requests and see what the response is, and then learn, okay, like this is when I send this thing, it sends it in this format, and so the things I'm looking for are here, and this is how I can parse this response. And you can basically, rather than having to have hard-coded APIs, you could have a few shot learner that just like really quickly learns like how to parse something, and then use that API.
Yeah. I was reminded of this because of Brett Victor's talk about the future of programming, in which he pretended like he was a programmer in the 70s and talked about the state of the art at the time, and basically it's just what we have today. And he was just optimistic, like surely in the future we won't have like programmers on one side implement an API and the programmer on the other side read the API and implement stuff on the other side. And so it was akin to like, how do you solve the problem of us meeting aliens and then finding a way to talk to each other, because like that's what a self-healing API would effectively have to do. Yeah, and I also read this back and forth between Alan Kay and Rich Hickley.
In the 2016 Hacker News thread.
Yeah, where they just talking past each other completely, and I think Alan Kay's whole thing was this notion that you would have to be able to build up an understanding of data between two programs that didn't understand each other at all by sending the interpreter across the wire along with the message. And Rich Hickley was talking about something else completely different, about like how data itself is important and that sort of thing. And so I don't think either one of them contemplated that maybe it could be negotiated with transformers. And so I've never heard of Alan Kay talk about machine learning at all whatsoever. So maybe it's out of his purview. I don't know.
Yeah, no, I mean, I think in the episode where we talked about this last time, he did mention this idea of alien communication and this thing called Linkos.
Yeah.
And so he doesn't say it directly in the thread, but there are vague implications that he is interested in machine learning to facilitate something like Linkos, to bootstrap a communication mechanism between two protocols that or two entities that have not agreed upon a protocol. And so, yeah, it's interesting, and it doesn't necessarily pertain to transformers per se, but there was this research study out of Facebook where they basically had two agents and they learned to communicate with each other and through their own protocol. So yeah, it could be interesting to see if you can have these generative models facilitate communication between the two entities that have not really communicated with each other before, provided that they are not encoding things in a completely arbitrary, crazy way, but rather in a reasonable way that looks like things that you might expect, but simply modulo some transformation.
Yeah, I think the thing I would worry about is like the reliability. Like, how would I know that a concept made it over reliably? And like, I don't want like some, especially if they're getting, no, I mean, either reads or writes. Like, how do I know that there isn't some misunderstanding? Is there some self-correcting way to do it? I guess that's a research level problem.
Yeah. I mean, I think so. Yeah, people are gonna have to figure out all those details, and it might not just be, just using transformers. They're probably going to have to use, error correction techniques or, other classical techniques as well. But
you're right.
Could be interesting.
How big are these models? Is it practical to stick it on each end of a client? It may not be unless they're like servers or something.
Yeah, they can scale arbitrarily. So there are versions of these transformer models like BERT that can run in your web browser as a part of a Chrome extension. But they can also be quite large, and it's only feasible to run in a data center.
Yeah.
So it depends on what level of performance you need, and so it might be feasible in some cases. I'm somewhat doubtful that you need a GPT-3 level transformer model to do something maybe simple like facilitating a small API transformation between machines or something like that. I think that you could get by with something smaller. So I think,
because you expect the API things, the language to be relatively regular and the data to be regular, whereas like human language tends to have a lot of exceptions and context involved.
Yeah,
why
that's
it's bigger?
my intuition for why you might not need the full power.
I
Yeah.
see. I see. Huh. Are there like other types of use cases that we haven't really thought of? One thing that came to mind was to generate teachers with these GPT-3 models.
Hmm.
And this is not completely out of the blue, but for those of you that have read The Diamond Age with the young girls and Kyridian, it's basically like this book that adjusts to the reader, and she starts off at a young age being to learn how to read, and as she grows older it teaches her more and more complex concepts. And the way that Neil Stevenson, the author of the book, conceptualized this was that there was an actor or a number of actors and actresses that are behind the characters in the book that teach her stuff, but you could conceivably have machine learning algorithms that would be able to generate this sort of stuff for you. So for example, if I want to learn more about, I don't know, quantum mechanics, I would then engineer the prompt to write stuff that help me understand the core concepts of quantum computing. And so maybe that would be a case. And so it could generate not just text, but maybe video or images that go along with it, and even code, like exploratory code that helps me interact with these core concepts. And so that seems conceivable in a hand wavy way. I don't know what the complexities are involved there. Maybe it doesn't generate very good ones because the embedding isn't quite right, but I don't know.
Yeah, no. So I think that's a really, really interesting line of thought, and I imagine the reason why you picked quantum computation is a reference to the mnemonic medium by Michael Nielsen and Adam Matsuchak.
We'll put that in the show notes, I guess.
Yeah. So it's interesting, right? So how do you make a type of medium where it adapts to you and allows you to learn what you need, maybe realizing that you've forgotten something or you didn't understand something and you say, I didn't understand what you just told me. Can you rephrase it again? Can you show me another resource that will perhaps elucidate it a little bit differently? And I see that there's a very, very huge potential for that, because there are transformer models that are being paired with huge repositories of data, for example, the entire corpus of web pages, and they people are researching ways that you can have transformers look up information in external repositories of data. So rather than having these transformer models memorize the entire data during training, you are able to steer the model to look up the answers in a third-party source. And actually, Google has a demo called Lambda, L-A-M-D-A, we'll put it in the show notes, where they have a UI that looks like a chatbot. It's powered by a transformer model, where you can ask it things like this. So basically, rather than using Google search and you finding all the answers in all the web pages, you're able to ask the chatbot, and it's able to pull in the web pages that are appropriate, show you the snippets when appropriate, show you a snippet of a video in response to your question, and basically respond to your query, not just as a one-off query, here's a bunch of resources, you go figure it out, but in this iterative way. And so I imagine that a textbook would potentially be similar in that, you wire up this chatbot to a textbook, to a lot of different styles of teaching the same material, resources on the web about that material, and then you're basically able to have a dialogue with it where it sort of figures out, okay, well, this is what you need to know. You clearly don't understand this aspect. Let me find a resource and pull it for you and show it to you.
Yeah, I wonder how well that would work. Because right now, realistically, even though we have like GPT-3, I can't imagine it working super, super well. I'm not exactly sure what the gap is. Because recently I was like looking at algebraic effects, and that led to a rabbit hole about category theory. And honestly, I can't read a lot of this stuff because I don't have the background in it yet. And like a lot of times I was thinking, if only, because like once you understand mathematical concepts, they actually embody a really simple concept. It's just that it takes so many words to be precise about it, and there's notation for it. And so it's hard to look that up sometimes. And so if you had GPT-3 or something to explain it for you as you're going through it, as a way of helping you understand the material, that would be very helpful. But for some reason, my intuition is that it's not quite there yet for something like that, but I'm not sure what the gap is.
My take as somebody who not only works in NLP, but in search specifically, is we're closer than you think.
Oh, that's awesome.
Yeah. So I actually think in the next couple of years, we're going to start seeing things like this. And I think it's going to be framed a lot in the language of search, but you can frame it in the language of a mnemonic medium, and I think that it would actually be a very good match for that problem as well.
Well, what gives you the confidence for it? Is it an intuition, or there's like some aspect, like what's in your head that's not in mine?
One is I've used early prototypes of something like this,
Oh,
and
okay.
they work really, really well. And yeah, the second is that, again, going back to the transformer, they're multimodal and things like that. I think I'm pretty confident that you could have, for example, when I was researching this podcast, of course I was going to the first primary sources, the research literature, but I was also trying to find, can I find an explanation of transformers that is visual? Can I find an explanation of transformers that is for the layperson versus just the researchers? And so I think that just being able to index all of the resources about a topic and then letting this model figure out how to pull in the resources is very feasible. So you can imagine typing to this transformer, can you rephrase this in a layperson's terms, or can you find me a more simplest version? And
have Chris Rock teach me about transformers. Yes.
Yeah, exactly. And so I think that all of those are in the realm of feasibility. It's just a matter of putting them together. A lot of it's going to involve very good engineering, but I don't see any aspect of this that is infeasible.
I see. At least from a technical standpoint, there may be other showstoppers, but at least from a theoretical feasibility standpoint, it is hard, not impossible.
Mm-hmm.
In engineering parlance, I guess.
Yep.
I see. Okay. So where do we go from here?
Yeah, I mean, I think we've covered a ton of ground on the transformer. I think that one sort of call to action I would encourage people to do is to actually just use a GPT-3. It's open. The API is completely open to the public now, and just try out different prompts and do prompt engineering. I think that's going to be a huge component of programming in the future, where it won't look like programming, but it'll look like, can we elicit answers from these pre-trained models? And then, I mean, we'll put a ton of resources in the show notes, but I think that the best way to get a grasp on the power of transformers is actually just to use tools that are based on transformers. And I think it's really, really exhilarating to see how good they are. You really won't expect them to be that good, especially if you haven't used some of these machine learning tools or you haven't touched machine learning in a few years. It's really shocking how good things have become.
Right. So, okay, yeah. I am excited for this world that we've, I guess, this cockamamie world that we've pulled out of our heads. So then, I guess, do you have any like closing remarks on the world that we're headed? Is it, I guess, like the thing that I see, if like all goes well, is that a lot of things that we previously thought were out of reach of our computational tools are going to be within reach, because we typically think of images and video and like other forms, or even generating code, as being inscrutable to code itself, and so, or machines themselves, and that's all going to open up, and that means that we can do translations from one medium to another, whether it's image, code, web pages, even like self-driving, or even like, I don't know, like process optimization, that sort of thing. And so you might end up having these entities run significant portions of our world, which I guess is one thing that we're going to see. And so I guess people losing their jobs is probably going to be perhaps the least of our concerns, but like these things are going to be shaping our world in ways that would make the Flash Boys, where seem like quaint, where like algorithms are shaping like whether we have a straight line for fiber optics between Chicago and New York, right? Like that sort of stuff will seem quaint.
Yeah. No, I think it's definitely going to be pretty crazy. I think that again, these models are multimodal, and so even if you don't work in a problem domain that involves text or that involves images, if you're working with graphs, you're working with ASTs, you're working with 3D point clouds and 3D models, all kinds of things are fair game with transformers. And the interesting thing is that you can use text increasingly to steer these transformers. So you can imagine having a generative transformer that generates 3D models for games, and
or
rather
the games
than
themselves.
that rather than building the games that builds the games themselves, and the way that you control it is by saying, can you make it more like this, or can you make it more like that? And so we went into that a lot with the DALL-E and creative collaboration. But yeah, I mean, I think that to be prepared for this new world, I think that a lot of the things that we used to think computers couldn't do, they can increasingly do. And so my other call to action is, once you've convinced yourself with using some of these demos of the power of some of these models, really try to imagine how you can apply it to whatever domain, even if you're not a machine learning practitioner. How can you apply this to whatever you work in? Because whatever field you work in, you have some type of data, you're manipulating some type of data, and so it's entirely conceivable that a transformer can be fitted to solving the problems that you have day to day.
Yeah, it's kind of the same problem that Zapier has. People understand what it is, but they're like, I don't have any examples in my head, and so like I need to go look at some examples. So yeah, like when you're playing around with GPT-3, check out some of the examples that they have to help your creative juices going.
Yeah. So I mean, obviously you can tell I'm super excited.
Yes.
How are you feeling?
I think this is one of those things where it both excites me and terrifies me, because I can imagine a world in which it gets strange really fast, especially like the things that I talk about where these machine learning models earn their own keep, and they might be the proto versions of things that live for a while, and so that sort of thing is weird. And you could have things that govern not just cars but an entire city or a nation state, perhaps. So that is weird.
Yeah, it's definitely gonna be a weird world, as sure these things can increasingly do things that we thought only humans could do. Yeah. So with that, this has been Shri,
And this is Will.
Thanks for listening to another episode of the Technium. We'll be back next week for yet another episode that goes into the edge of technology. Make sure to like, comment, and subscribe. We actually got our first comment the other day, and
exactly.
Very, very interesting content there. So we'd love to hear more from you. And again, thanks for watching.
Yep. Take care. I'll see you next week. Bye-bye.